Thank you for giving me an opportunity to give this talk, even though I couldn't come in person, and it looks like a great meeting. I'm sorry I'm not there. So I understand this late in the conference. I don't need to give the introduction, but just to set the common kind of stage. I will be talking, of course, about 21 centimeter cosmology with hydrogen atoms and from the whole cosmic dawn and ionization era. So focusing on the formation of first stars and first galaxies and their observability with existing telescopes. So what can we say already about today about these objects? And of course, the beauty of 21 centimeter cosmology is that it is sensitive to basically every hydrogen atom in the universe, and it's a probe of this whole iceberg. So it's all galaxies and most sensitive to the typical stars and galaxies in the universe. So in the sense, it's complementary to probes such as JWST, which can only observe very bright galaxies. 21 centimeter, as you know, is dependent on many processes, and it's very rich in physics. We can study stars and galaxies and conclude about dark matter physics using it. Use it as cosmological probe, as Rajesh just described. Study growth of structure, formation of the first dark matter halos, heating processes, process of ionization, binary stars, and in that way it's related to gravitational wave formation as well. Quasars through ionization and heating. It can probe metal enrichment history and any exotic physics that there is. So it's really a rich probe. And at the moment, I'm really curious about what can we say about very first stars with it. So just to set the stage again, it's mostly sensitive to this contrast between radio background and gas temperature, as you know. And there are many processes that affect it. So neutral fraction is roughly 1 at high redshift, so through cosmic dawn and most of through cosmic dawn, and then drops drastically during ionization. But this observability of the signal especially is boosted by lambda alpha from stars, which peaks up as stars start forming at the onset of cosmic dawn. And at that time, we can use this contrast between gas temperature and radio background to kind of think about 21 centimeter. So it's due to star formation that the signal actually becomes observable. And of course, it's non-uniform, and every type of radiation has its own effective horizon. So star-forming regions that are very rare at high redshifts will imprint these bubbles, but it's bubbles on different scales. So say ionizing bubble will be very small, or very close to star-forming region, while heating bubble can be on scales of few hundreds of megaparsecs. And lambda alpha coupled bubble is a few tenths of kiloparsecs. So it's a rich structure of these bubbles that are imprinted eventually in the 21 centimeter signal. Sorry. So what can we actually tell about the very first stars using this line? At the moment, we know very little. There are people who do really sophisticated simulations of star formation. And that's the slide from a recent review by Klassen and Glover shows our state-of-the-art knowledge about this initial mass function, so the distribution of stellar masses of these objects. And as you can see, different people predict different things. So it can be anywhere from subsolar to a few thousands of solar masses. And it is still not clear if that's just the physics that people use, or it's also the inherent properties of the stars. So the question is, can we clear this picture using 21 centimeter signal from cosmic dawn that many people are trying to observe now? So we did a series of papers with my students, this one led by Thomas Gacy-Jones. And so first of all, we focused on the Lyman alpha-driven effects, such as Wolfshausen coupling, Lyman-Warner feedback, and Lyman alpha heating. And Thomas did a very thorough study of using zero metallicity, so for population 3 stellar evolution tracks from MESA, from our collaborators. And then he ran this through Telasty, which is stellar atmospheres code, again at zero metallicity, to create spectra of the stars as a function of stellar mass. So we had a very broad range of masses from 0.5 solar to 500. And on the right, you see an example of how the properly modeled spectrum differs from the black body assumption that we used previously. So ballpark is the same, so there is the same order of magnitude, luminosity or flux, but there are, of course, features and details that vary when we properly model these emissivities. So, and then we took several typical IMFs, initial mass functions that people study, from very flat and top-heavy, like this red one, to a very salpeter-like, which is more similar to what stars are today in this blue, and several intermediate versions, and convolved this study with initial mass functions to obtain population spectra. So here on these panels, you see how the spectra vary as a function of initial mass function versus time. And it's very different, and there are several reasons. So when we only have very massive stars, they are very big and they live shorter, they are brighter and burn faster. And so after just a few million years, the spectrum drops to zero, but during this few million years, it's very bright. While for more salpeter-like case, on the top left, it is more spread over time and less bright, but the stars will influence the signal through longer period of time. So when we just take into account these three effects, so with Thousand field coupling, Lyman alpha heating, and Lyman-Warner feedback on star formation, we get this 21 centimeter signal. So on the left is the global signal, on the right is the power spectrum. And we see that for a population that has only one stellar mass, so all stars would have just one mass shown on this color bar, signals in the range of small stellar masses. So if they're dominated by small, a population dominated by small stellar masses, signal will differ from each other. While in this realm of high masses, above 20 solar masses, all signals merge. And this is because there is this, the stars become very short-lived and bright. And in the eyes of 21 centimeter signal, they all look the same. So it is, in a way, both encouraging and discouraging, because we can probe small masses, but probably first stars were massive. So this shows that the signal wouldn't be useful. However, here we only took into account the Lyman alpha effects, and we know that 21 centimeter has several effects that affecting it, in particular X-ray heating, ionization, and we want to take the signature of initial mass function further through these processes and add up together to see what is the eventual role of the initial mass function on 21 centimeter. So we have done that as well. We looked at X-ray sources, and we know that very long, long wavelengths X-rays would have low energy, and they won't propagate far. So it's this low bottom half of the screen picture. When these photons imprint very strong fluctuations close to the sources, they inject all their energy just around star-forming regions. And the mean free path in this case is around is a few megaparsecs. While if we have very energetic X-rays, they can travel large distances, a few hundred megaparsecs, and create very washed out fluctuations like on this top plot. So the question is for the population 3 binaries. Of course, there are many uncertainties, but we can try to model their X-ray spectra and see how, depending on the initial mass function, the spectra would vary. So this is exactly what we did with Nina Sartorio, who was my postdoc, and she did the population synthesis for X-ray binaries, taking the same MESA evolution tracks and propagating them through binary population synthesis called binary C. She wrote the X-ray model in binary C that creates X-ray output spectra from each population. So this is her result here. We see that depending on the initial mass function, so she took a kind of low mass initial function in yellow, high mass or top heavy in black, and an intermediate one in red. We see that the spectra vary quite a bit. If a population is such that most stars are small mass, they will create many small mass binaries, but this will be not very efficient heaters. And we see that in such case, the X-ray spectrum is very low, this yellow line. In the case when there are few big stars, there will be few bright X-ray binary systems. So X-ray signal is stronger, but actually a sweet spot is reached when we have an intermediate initial mass function. In that case, we have a large number of rather efficient binaries, and they add up to a very strong X-ray signal, so this red line. And the dotted lines here show absorption by hydrogen around star-forming region. So the dotted line is the spectrum that will reach the intergalactic medium. So the question now, if we add to the Lyman alpha signatures the effect of initial mass function of population 3 stars on X-rays, we will get a more observable signal. And again, with Thomas Gacy-Jones, we did that. So he did that by adding X-ray spectra consistently with X-ray luminosities calculated using the proper initial mass functions to the signatures of Lyman alpha photons, and explored the 6 different IMFs here on the top right of the top left of the screen. So we have purple, which is salpeter-like. Yellow is very top heavy, and we have several intermediate versions. On the top right, these are X-ray spectra that we get for each one of these populations. And on the bottom, you see actually global signal on the left and power spectra on the right. And the interesting thing is that actually all IMFs give very different predictions. So in principle, there is enough information in the 21 centimeter signal over a very large redshift range from the moment stars are created at redshift 30 all the way to redshift 10. And here we didn't take into account reionization yet, the effect of IMF on reionization. But through the joint effort of Lyman alpha photons and X-rays, this population 3 initial mass function signature is imprinted in 21 centimeter signal over this very broad redshift range. So of course, here we had to fix all other parameters. So we have population 2 stars, population 2 heating, transition between population 2 and 3, and reionization, sorry. And we had to fix all these parameters. So the natural question to ask is, of course, we don't know what these parameters are. And if we vary them, do we still get to detect this initial mass function? And that's exactly what Thomas did. We did the Bayesian analysis, so varied all parameters in a very broad range, except for initial mass functions. So the 6 different initial mass functions were kind of hypotheses, and we checked if each hypothesis can be proven right or wrong. And it turns out that if you take a flat IMF as the truth, then all other population 3 IMFs can be discarded or rejected, both with SKA or with a global signal experiment such as REACH. So REACH with a 25 millikelvin uncertainty would be able to reject those at more than 3 sigma, and the SK with 3,000 hours as well. So here treatment was not of SK and REACH was not very fair, because for REACH we took an optimistic case and for the SK epistemic case, but we just wanted to see if in principle the POP3IMF can be detected, and the answer seems to be yes. Of course, there are many modeling uncertainties that we need still to play with regarding star formation and binary formation and X-ray luminosities and so on, but this is a very encouraging result, I think. So this is in the future, but what can we tell about our models and high redshift the universe using existing data? That's also an interesting question. We get more and more data from LOFAR, HERA, SARAS, and rich staking data as well, and other experiments. So what are the current limits? So we have done a study here led by Simon Pochinda, where we use this model with population 2 and population 3 stars without the effect of X-rays implemented yet. And we looked what this HERA and SARAS 3 can tell us about population 3 star formation efficiency. And we see that if you see the posteriors here, that there is a very weak preference to low POP3 star formation efficiencies already with existing data. So that's also very encouraging. So in this study, we looked at 4 data sets. So one is HERA, SARAS-3. We looked at upper limits on unresolved X-ray background with Chandra and upper limits on the radio background with LWA or RK2. And we did synergy of all these data sets together. Simon showed that all of these data sets contribute. So this is kind of how the prior range of our model shrinks with each data set individually. And even very weak data sets such as radio background does add some information. And when we add all these data sets together in synergy, we get the strongest limits. So we explored how the posteriors of signals. So in gray, you see the posterior of models that we explored. So power spectra and global signals on these intermediate panels, how they shrink with each data set added. And in blue is the joint analysis. So there is quite a bit of ruling out of the parameter space that we explored. I should say here we used models with added radio background from galaxies. And the most interesting limits, I think, are on X-ray luminosities of high redshift galaxies, which we managed to constrain from both directions. So on the low luminosity side, 21 centimeter data plays a role because very weak X-ray heating would create deeper 21 centimeter signals, and these are easier to rule out. So we rule them out. While on the very bright side, unresolved X-ray background will constrain very bright sources, and we also rule them out. So we start seeing kind of measurement of high redshift X-ray luminosity. And of course, now we have JWST, and my PhD student Jiten Dhanha put this paper out just a couple of weeks ago on the archive, where to these 4 data sets, we also add UV luminosity functions observed by JWST and HST as well. We use a flexible model for population 2 star formation, and what Jiten did is to constrain parameters of this model using UV luminosity functions, but also in synergy with HERA and SARAS-3 and Chandra and LWA data. So in this model, we have, of course, a cutoff below some critical mass when stars cannot form. We have suppression at the low star formation of the low mass halos. There is overall amplitude. There is a point kind of transition between this flatter regime and the enhanced star formation at higher halo masses. We expect to have a peak and a drop when we go to even higher halo masses, but this will not be relevant for the high redshift that we are exploring. So we had the cutoff we just had one power law at the high mass regime. And so the question is,
you have 5 minutes.
Yes, yeah, thanks. The question is, what can we say about this model and the rest of the parameters when we add JWST observations to the mix? This is a kind of the parameter plot. Well, I just wanted to flash it. I'm not going through all details, but the interesting things to see is that we have a constraint on population 2 star formation efficiency, which is the normalization of the efficiency. There is some weak constraint on this M0, which is transition between low mass to higher mass halos which form stars. And we have tighter constraints on X-ray luminosity and radioluminosity of the galaxies than before. In this model, we still didn't have population 3 stars. That's something we will do in the future. We focused on population 2 because that's the range. These are the stars that majority of the stars that JWST UVLFs can probe. One interesting thing that G10 found is that actually redshift evolution of star formation efficiency depends on redshift. So if we only take a low redshift set up to redshift of 10, this beta star parameter that you see on the right peaks at, this is probability distribution, and peaks at 0. So saying that there is very little redshift evolution at redshifts lower than 0, but at redshifts higher than 0, so we have 10 to 14 redshift UVLFs. We find quite a significant redshift evolution in star formation efficiency. And that's consistent with what some other people found before us. A nice thing that G10 done is to calculate posteriors of both luminosity functions and the star formation efficiencies. So here on the right are our population 2 star formation efficiencies constrained by all these data sets together. And we see that in the halo mass ranges above 10 to the 10, there is quite tight constraint, but there is very poor information for lower mass halos as expected, and there is some redshift evolution as well here. And then I will stop here with my conclusion. So 21 centimeter is a very interesting probe and can even probe population 3 in show mass function in the future, which is very exciting, as well as heating processes and other interesting science. And I showed that we already have interesting data from HERA, SARA-3, other experiments, of course. We just used HERA and SARA-3, but LOFAR has similar constraint in power to HERA. And we managed to rule out bright radio sources, bright and very inefficient X-ray sources, and also made promising predictions for population 3 star formation. Thank you. I'll stop here.
Thank you, Anastasia. We have time for questions. Maybe I can ask one. Anastasia, when you, in the last part of the model, where you have, where you showed that you need the star forming efficiency to evolve with redshift. What do you do for other efficiency parameters like X-ray, and those also need to go into the model, right? Since you are
yeah, we have all of them.
But do they evolve also, the other efficiency parameters?
That's a good question. We focused on star formation efficiencies here in this paper. I think they don't evolve that much. We have it in the paper, but I didn't put it on the slide. So the most interesting one that, so for example, population 2 intensity, star formation efficiency doesn't evolve. So here we split all the data set into this low regime, low redshift regime and high redshift regime, and looked at star formation efficiency parameters. So F star 2, this transition point, the power law, and this is a redshift evolution parameter, and only redshift, so it's how this star formation efficiency evolves with redshift. Only this this kind of parameter showed a very distinct behavior. The rest, even for star formation efficiency, are similar. And we have a plot in the paper with the rest, but I don't have it here. So there is not much evolution in the rest as far as I remember. But we should double check. If it's not there, we will need to check.
No problem at that. Yeah.
Hi, nice talk. So I was curious to know, like, when you're using this JWST, so have you also like used the HST data set also?
Yes. So these are all the data sets we use. So just two papers, Bowman et al. 21, which is with HST, and then the Donan et al. 24 is JWST. So this purple data is from HST, and the pink ones are from JWST.
Okay, so I mean, when you are estimating your likelihood. So at the time you are considering like jointly all the HST and JWST, or I mean, have you checked the separately? Because
yes, we checked separately as well.
Okay. So did you find anything? I mean, weird, like the HST actually it's giving some different inference, and JWST is giving some sort of different.
No, we only found this. So if we include all redshift points up to 10 in one set and 10 to and above in the other data set, we have this split in behavior. But other than that, we didn't. Everything is consistent.
Okay. Thank you.
Thanks.
Okay. Any other questions? If not, let's thank Anastasia again.
Thank you.